Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. Isaac Newton's famous book, The Mathematical Principles of Natural Philosophy, might as well be called The Mathematical Principles of the Art of War, because the nation whose officers are best trained and most highly skilled in applying these mathematical principles usually win the war. So today we're having a look at section 7.5, number 7, and it asks to calculate approximations to the following integral. And so we're interested in the integral from 0 to 6 of x squared dx. And since this problem involves estimates, left-handed estimates, right-handed estimates using the rectangle approach, as well as the trapezoid approach and the midpoint approach, we're going to take the camera over to the computer and we're going to demonstrate how to solve this problem using Calc tool. And it's important to become comfortable with technological tools because cadets at the Air Force Academy need to learn how to use technological software with all the skill and enthusiasm that high school students learn new video games. Okay, we have Calc tool 2 up on the screen, but rather than using the graph tab in the usual way, let me call your attention to the Riemann sum tab, because the Riemann sum tab has all the apparatus to work this problem. And also, to help the screen display be a little clearer, we're going to change the line width to 3, and we also need to think about the domain of the problem. So the domain, or the limits of integration, are 0 to 6, so it might make sense to adjust the domain of the graph to go outside that just a smidge. So let's have the window on the graph go from -2 out to 8. And the function is x squared, so we need to give a little thought to, as x goes from 0 to 6, what does x squared do? Well, x squared is going to go from 0 to 36, so let's have our y window in the plot go from, say, 0 to 40. So all the curve that's of interest to us ends up in the window. So now we enter f of x equals x squared, and we can hit the graph button, and we can see that, as we expected, x squared is a parabola, and the red curve designates the function, and the blue rectangles are the area estimates that are going into the Riemann sum. So lots of slides and boxes over here that we need to attend to, and it tells us the problem to have two intervals, so we make n here equal to 2, which happens to be what it came up with at the beginning, but we need to change our interval, and our interval is from a to b, and a is 0, and we want to make b equal to 6 because b is our upper limit in our interval of integration. So now what we have is we have the rectangle selected, and this is the left-hand sum of rectangles over the interval. So our first rectangle, the input value, or the height of the rectangle, is 0 because the left hand of that curve is 0 and the width is 3. And then our second rectangle also has a width of 3, and its height is governed by the output of the function at the left-hand part of the interval. So it tells us that the net area is equal to 27 in this case. And that's not a very accurate estimate, because when you only use two rectangles in these Riemann sums, it's never very accurate. So why don't we just bounce up to 200 real quick, because as you get a sufficient number of intervals, a sufficient number of rectangles, the different methods of estimating these integrals become more accurate, and they also become closer to each other. So when we use 200 rectangles rather than 2, the net area is 71.4609, and I suspect that as we have more and more rectangles, that area would converge to 72. Alright, but let's go back down to two intervals because that's what the problem asks us to concentrate on most. But now, for part B, it wants us to estimate the integral using the right-hand method. So we click on right, and now we see that we have the left-hand most rectangle, or the first rectangle in the interval. Its height is governed by the output of the function at the right-hand side of the interval. And the second rectangle, its output is governed by, or its height is governed by the output of the function at the right-hand side of the interval. So we can see that the net area, which is our estimate for the right-hand method, is 135. So it's pretty much an overestimate because, as you can see from the figure, the rectangles are counting lots of area that really isn't under the curve. Alright, so now we can turn our attention to part C, which says use the trapezoid rule. And when we use the trapezoid rule for the two intervals, it draws these two trapezoids. In the left-hand one, the trapezoid kind of becomes a triangle because the height on the left edge of the trapezoid is 0. But then the second trapezoid is a normal trapezoid in the usual way. And the estimate of the trapezoid is 81, much closer, but still something of an overestimate because there's some area here under the trapezoid that really isn't under the curve. But we can do the same thing with the trapezoid that we did with the left-hand integral, namely make a whole lot more of them. So if we make 200 trapezoids, now we can see that the net area, which is the estimate for the integral, is 72.0009, which is much closer to our expected value of 72 than the left-hand rectangle was for 200 intervals. Alright, well that covers parts A, B, and C. And now let's use the midpoint rule. And to use the midpoint rule, we select rectangles again, and we click on the mid slider, and it tells us here that the net area is 67.5, which is closer than either the left hand or the right hand rule when you're only using two intervals, but still not as close as it could be. So we can also take the midpoint rule using rectangles out to 200 intervals as well, and we graph that, and now the midpoint method gives an area of 71.99955. So Calc tool is a very powerful tool for creating numerical estimates for definite integrals using the left, right, and mid rectangle methods, as well as using the trapezoid methods. And so we can see that when we use a small number of intervals, our estimate is rather poor, but then when you balance it out to 200, or you can even go to 2,000 intervals, for most reasonably simple functions, it produces a rather accurate estimate of the area under the curve, which is the value of the integral.